Hello, everyone. It's an honor to be here. And this talk is about how to take over an Samsung SmartThings hub with a single API call. And I'm Chen, a security researcher at DEVCORE. And if you have any questions or feedback, you can contact me by email or X. And before I start, a quick reminder. This talk is basically at a hardware DIY level, so there's no hardware hacking. And you might have noticed the picture is of an Aeotec smart home hub rather than SmartThings. So what is the Aeotec smart home hub and how is it related to Samsung SmartThings? And why did we choose it? We picked it because it was another Pwn2Own target. Last year, we decided to participate in Pwn2Own Ireland. And at that time, we had a big team, full-time researchers plus interns, more than 10 people in total. And there were only 23 targets. So we have a good coverage after everyone picked someone they were interested in. I also took a few devices to research, but I thought it was a good moment to take a risk because we have a lot of people. Especially, it was only August. We had 2 months for finding vulnerability. And after a brief review, there were 2 categories that no one had picked yet. I chose Aeotec Smart Home Hub because I assumed it would be the easiest one among others. And in the end, we had exploits for 9 devices, but one was fixed before the contest. We were also the only team to report a vulnerability in the home automation category. So, what is the Smart Home Hub? It's a command center of a smart home. A user can control all the devices from their phone. And the hub supports most mainstream protocols. So with one hub, you can control a wide range of smart devices. From the release notes, we learned it shares the same firmware as Samsung SmartThings. And the hardware is also the same. It's actually a rebranded Samsung SmartThings Hub V3. So, how do you interact with the device? There's no way. After setup, you just see a green flashing LED, and that's it. Sure, the user can control it through the smartphone app, but all they see is, oh, it's connected. And if you tap the device, it's still connected. There's a drop-down menu at the top right corner with options like drivers. You can see the installed drivers. At the device, you can rename the hub. In settings, you can set the Wi-Fi, firmware update, Zigbee, Z-Wave. In the information, you can see the device info. That's it. So I think it's port scanning time. Then, the only thing we saw was a 503 service not available on port 443. So this is what we knew at that point. How to interact with it, no idea. Port scanning result, no useful info. Maybe we should try downloading the firmware for analysis. But it's not provided. What? So we decide to literally bunk it on the head. It's a little bit hard to open the hub if you tried before. But after we open it, we found most components are on the front side. We could directly tell what models the components are. And then on the back side, it was obvious that there is an UART, so we soldered a pin header, then power it on. In the console, we saw that hub core had an executable stack. That means once we control the execution flow, the game is over. Just run the shell code and get the shell back. It looks extremely promising. But the UART was read-only. We couldn't get the file system or an interactive shell. So we decided to get the file system from the eMMC. But how do we get it out? The usual method is to hit the eMMC with a heat gun, remove the chip, place it into a socket, and read it with a PC. Sounds good. But the problem is after removing the eMMC, the device wouldn't boot. So we had to put the eMMC back. But the chip is super tiny. The size is 10 millimeters by 11 millimeters. And we have to make sure that all 153 pins are soldered correctly. So after that, we have to align its position on the PCB by eye. Then use a hot air gun to melt the solder again. It's painful Because I'm a noob and afraid of breaking the device, I tried another approach. I learned that the eMMC is actually an SD card embedded in the PCB. With strong wire and an SD sniffer, we should be able to read the eMMC. To do that, we need these tools and a pair of good eyes because everything is hair thin. Okay, so we must find at least 4 pins to run the card in low speed mode. They are command, VCC, clock, and data 0. To identify the pins, scratch the PCB to expose traces, analyze signal with logic analyzer. Then we can recognize the clock and VCC, but we couldn't tell the difference between command and data 0. To clarify, we try to figure out the layout from the SOC. From the SOC datasheet, we located clock at D8. And all the other pins we wanted were around it. So, now we knew which one is data 0 and which one is command. We solder jump wire to the corresponding pins on the SD sniffer, fasten them with some tabs, and you will get something look like a space battleship. Then we plug it into a computer. We got nothing. So I thought I have the wrong VCC. Maybe the VCC is for other components. Then I thought, how about just powering on the PCB? But the SOC, we operate the eMMC, and that's not what we want. To avoid that, I cut the command and clock, so the SOC couldn't talk to the eMMC. And let's try again. Still nothing. Maybe an impedance matching issue? I'm not sure, but I definitely look stupid. But yeah, I thought I can handle it after just watching few tutorials on YouTube. But seems like we still have to desolder the eMMC. So we bought some more tools and apply flux, desolder the eMMC, clean it, place it into a socket, read it. Hooray! There were 3 partitions here. How easy is that? So, after I got the firmware, I called my colleague, HexRabbit, a kernel CTF master, to help me to see if we could find anything interesting in the file system. Though there are 3 partitions, only 2 mattered to us. The partition 1 contains a standard fit, and the partition 2 contains an encrypted file system. Standard fit had 4 items: Linux, opt, RAM disk, and FTD. That means the device has a TrustZone. Linux is the normal world, and the opt is the secure world. In the normal world, the system calls a getKey function to get the key, and then use it to decrypt the file system on partition 2. So where does the key come from? Can we decrypt the file system by ourselves? In normal world, the getKey function executes a binary, looks path, which asks the Linux kernel for the key. The kernel asks opt asks a trusty application for the key. And then, the key is stored in the RPMB, a special block on the eMMC. To get the key, all we need to do, just read it. Okay, we just read it, but the key stored in RPMB is actually not the looks key. It's an encrypted looks key, which is encrypted by the opt. Opt will decrypt the encrypted looks key using the file encryption key, FEK. The FEK is also stored in the RPMB. Also, it's not a file encryption key. It's encrypted file encryption key. Encrypted by the TA storage key and derived from security storage key, derived from hardware unique key. That's stored in ROM of the SOC. That means it's stored inside this thing. Every hardware unique key is, of course, unique. So we can obtain it by static analyze from our laptop lab. Can we get the key dynamically? Since the system reads the key, then decrypt the file system. Why can't we just get the key right there? So we try to modify the script so it would print the key for us. When we try to build the standard fit with the modified script, we found that, shoot, the fit was signed. Of course. The SOC supports the secure boot. However, my colleague HashRabbit hypothesized maybe securable wasn't enabled, we can test that by overwriting a U-boot string with a boot string. I didn't think it was worth trying. It was very likely we only get one shot at flashing it because we are so noob. We probably break it on the second trial. So probably a dead end. I think we're doomed. Or is it? When I was thinking, can we use some fancy for injection to bypass the check or something? HashRabbit checked the version of the U-boot. Oh. What? Sorry. It was U-boot 2017. And is it okay? Yeah, sure. It was U-boot 2017. And there's a CVE. That is CVE 2020-10648. Actually, standard fit contains a config that includes a signature. The config tells U-boot what to use when power on. The signature is the hash of everything, and the vendor signed it, so it's supposed to prevent tampering. But because of the vulnerability, if we take a signature from a valid config and append it to a malicious config we created, the check passed. U-boot doesn't ensure the signature corresponds to the specific item being used. When opt hands control to Linux use our malicious RAM disk. So we can implant a backdoor. Now we knew how to proceed, but it was 6 o'clock. So do you want to burn some extra hour to get it on? The answer was definitely yes. We already prepared the tool that morning. We put the eMMC under a fixture, apply solder path by tools, or you can by finger, but I don't recommend it. Melt it, let it cool, and we successfully boot the device again. It took until 3 a.m. Didn't we start it from 6 o'clock? Why it takes so long? Because though it looks perfect, the eMMC was actually not flat. Plus, everything is a little bit sticky due to the flux. And align the eMMC with the white frame on PCB was painfully difficult. And everything is hot as hell. But anyway, we were ready to read the key from UART. Then we hit a syntax error in the script. Oh, because we forgot that calling the function in bash script doesn't need a parenthesis. Okay. So the moral of the story, practice is still needed when it comes to command injection. So we started over, went through all of this. Then we got another message. The get key command does not give a real key on this platform. What? So the password is actually 0? But that's not true because we already tried that before everything. So what actually happened was on boot, Linux from partition 1 decrypt partition 2 and mounted the decrypted file system as hub. Then it will change root to hub. But somehow the script tried to call get key after change root. So the command can be found. This behavior was not modified by us. We just add some print command after get key function. So that means there was definitely something broken. Something is using 0 as key. But we didn't have time to exploit that. So we just print the key earlier in the boot sequence to get the correct key. Yeah. So start over again. Now we obtain the real Lux key for the encrypted file system. And everything was done at 9 a.m. So we got the Lux key on September 6th and implemented a reversal on September 12th. We still had a month left to find some vulnerability. So back to service, port 443. It was forwarded to the port 8080 of localhost by LightTTPD. And besides this, there were 2 more ports, 8766 and 9495. We parsed the URL, and they all require authentication. Let's focus on 9495 first. Remember that the user can control the device via phone, right? That means it also needs authentication. So there is also a token. By pure guessing, that token is work on 9495, which suggests 9495's authentication goes through the cloud. So it sounds it's not a good target for us. Let's just put it aside. What about the port A766? It returned an error message which gave me an idea, all about giving it a random JWT, but with algorithm none. So I encode the request and send it to the endpoint. We got 403, authentication failed. But the response include an error message, scope not authorized, require rHOP's PIN. I put rHOP's PIN into my JWT and try again, but still 403. And the same error message. Was the error message because algorithm none wasn't accepted, or because the key value pair of scope was wrong? It was time for some real reversing. Then, after 3 weeks later, I realized it was impossible to reverse the binary. Okay, at that point, we knew that A766 and 9495 are handled by a binary called hardware. A hardware is a huge binary that handles most of the device functionality. In the first place, I thought it was written in C. Later, I found Rust code inside. It even contained Lua. What? And even worse is there is a function responsible for initialize everything for Rust. The size of that single function is 362 kilobytes. And it took hours to decompile the function in IDA. Then it produced 76,000 lines of code. So it's impossible to reverse the structure. That means it's also impossible to reverse efficiently. However, the solution was extremely easy. Just swallow your pride. You are not a security researcher anymore. You are a string analyst. So, by analyzing string, we learned there are 4 web servers inside hardware. The first one is 9495 I mentioned earlier. And the second one is the one we block it by the authentication. The third one is a little bit weird. It is also an Aeotec web server, but doesn't listen on any ports because it's connected directly to Samsung Cloud. When user control the smart home hub on phone, Samsung Cloud redirects the request to that web server. And the API endpoint on the cloud are identical to those on the hardware device. Home hub device. And the last one is listen on 8080, which is not active by default. That's why we kept getting 503 service not available on port 443, because it is unavailable. So it was still hard to understand every details about the device because all services are embedded in hardware and multiple services exist. So it's hard to separate routes per server by string. The JWT validation logic was also difficult to trace. However, I still caught Samsung sleeping. Only 10 days left for registration at that point. Okay, so what I found was a function containing the string token, followed by a help message explaining a token command. It's odd because there is no shell or shell-like environment exposed to users. The last line of the help message caught my eye. The help message said, it will generate token for hop local API. What is hop local API? The A766 port is named hop local API in hardware. The token command is in the command class for the telnet service. It's also not active, but we can use GDB to jump to the function. Okay, using that approach, we obtained a valid JWT. Turns out the early error message was misleading. The required scope was hop R pin, not R hop's pin. But anyway, even if we can guess the scope correctly, the JWT still had a signature. We generate a new JWT after reboot. The signature changed, which means the JWT key was not fixed. With the new JWT, we got HTTP 200 from util pin. But what if we use the old JWT from previous boot? We still got 200. Is that because the database was not wiped? That's wrong. This time, we use the old JWT without a signature. Oh, it still returned 200. So it's basically just a base64 encoded string. Yeah, okay. Now, we want more than a pin. We want something more interesting. For example, factory reset. But the same trick failed. The endpoint returned an error message. HTTP client error, unauthorized. According to the error message, we thought the device will authenticate the JWT with Samsung Cloud for certain high privilege commands. It sounds a little bit weird, probably a fallback. Yeah, it turns out my assumption was correct. We could see there was a local permission error in the log file. Principal not found in inventory. Inventory means inventory DB is a SQLite DB on the device. There are two results in permission principal. But even after adding those principles to the JWT, we still got errors. From the string in hardcore, I guessed that the principal should match these two regular expressions. So this is the correct form of the principal in JWT, and it works. But you might have already spotted the problem. There is an IAM, which means the UUID is probably related to cloud accounts. And yes, each Samsung account has an unique UUID. It's stored on the device at setup. It's almost impossible to know the UUID during an attack. And as you can see, in both the regular expressions, they all contains the user UUID. But once again, by pure guessing, we learned that the device UUID can also be used as the user UUID. So, now what we can do is reset the device by sending an API request, then rebind it to our own account. Let's turn the problem into a jailbreak challenge. We could try installing drivers or attacking wireless protocols, for example, Thread or Wi-Fi. But when we tried to reset the machine, we found we also need a serial number to bind the device. The app asks you to scan a QR code or type the serial number manually. The serial number is printed on the bottom of the device. So we had two problems. First is how to obtain the serial number and how to get a shell after reset. We asked ZDI if we could get the serial number before we start our exploit. The answer was no. But the serial number was actually leaked in the picture I shown you earlier. The name of the thread network includes the serial number. So we scan the thread network with a thread device and confirm the serial number could be retrieved from thread network. Problem solved for the serial number. The only problem left was how to get the shell after a reset. Sure, we could attack these protocols, but there was only 2 days left. Instead of attacking those wireless protocols, we choose to have a look on the edge driver. Edge drivers are listed in the driver's UI. And the user can develop drivers in Lua. By creating a test channel, user can install a customized driver on their device. That means we can run any Lua code on the hub. So we tried OS execute immediately and read the log to see if anything happened. But we got an error. It said that the OS package doesn't have an execute function. Again, by watching streams, we saw there was a sandbox. The loaded package was overwritten. Dangerous functions such as execute in OS was commented out, so the edge driver couldn't use them. And the function required was also overwritten, making it impossible to reload the full OS package. So the problem was how do we retrieve the original OS package? Luckily, the load packages included a debug package. In Lua, every function is actually a closure because it captures its environment through a special variable. And the getUpValue function in the debug package can be used to retrieve the env, the special variable of a function. That means if any function captures the original OS package, we could retrieve the execute function from the original OS package using getUpValue. And yes, there was such function. The trim function in memory is declared before the loaded package was overwritten, so it captured the original OS package. The package .loaded.os.execute is not overwritten in the env of trim, so we retrieve it using debug.getUpValue. Could we get the shell now? Not yet, because there is an NSGel. Most of the syscalls were banned, and we couldn't access the real file system, but we found a possible escape via core dump. The core dump handler is a custom binary dumpster minidump. In the dumpster minidump, it checks if the process is included in a whitelist. If the process is in the whitelist, it executes create log package. In create log package, there is obvious command injection. But to reach it, we had to fulfill the whitelist constraints. That means we want to make the return value of the grep command become 0. If we look closely, you will find that there is an argument injection in the grep command because it forgot to use double quotes. And I have to mention, due to kernel implementation, the proc name cannot be longer than 15 bytes. To make the return value of grep becoming 0, we use argument injection to make grep print the version info. So that cost 3 bytes for -v space. To close the quote for command injection in create log package, we needed 4 more bytes. Now 8 bytes were left. 8 bytes for command injection sounds easy, but because what we're controlling is a file name, we cannot use slash. But we can still use $ single quote \x2f single quote to get a single slash that costs 7 bytes. And the currently working directory is root and it's read-only. So we have to craft a one-shot command that runs arbitrary commands without writing files. And my colleague immediately came up with a cursed method that is a recursive list, then pipe the result into a shell, so it will run every command. Technically correct, but we actually want is a reverse shell. Then orange came to the rescue. \curl0 backtick. The command would hit the 80 port for localhost, then use the backtick to execute arbitrary commands. Very, very elegant. And yes, the edge driver allowed you to listen on a port. Though the port number is random, but we can still spread it until we got port 80. So can we have our reverse shell now? Well, yes, but actually no. Because we broke our old device and we tried to escape from NSGel on the new one using a black box approach. Plus, most of the directories were mounted as read-only or non-execute. So we couldn't find any way to execute a binary in the end. So the only thing left to do was crying. But I didn't give up. First principle thinking was the key to solve the problem. What is the first principle thinking? It means breaking things down to the most fundamental truths. What is the most fundamental truth in our situation? That is, what is Pwn? It means to conquer or get ownership. And so I asked Orange, what do you think counts as Pwn? I made the hub mine. That's Pwn. But nothing can hide from Orange. He saw through the trick. He's like, oh, are you kidding me? But I still convinced him to ask ZDI, the real judge here. And that was 2 days before registration ended. Okay, there was only one thing left in our checklist list, right? Actually, no. The other problem was we need a thread device for scanning. You're probably thinking, what are you talking about? Didn't we just scan the thread network to see the result? Yes, we do have a thread device, but Orange doesn't. And it was impossible for Orange to get a thread device before the contest began. The only solution was for me to fly to Ireland with the device, which a little bit expensive. So, while I was thinking the solution, we got an email. ZDI accepted our interpretation of Pwn, so we didn't need to escape the jail. Let's update our dream plans. First, we reset the device via API. Then we bind the device to our phone, install an edge driver that serves a web page. The final result will look like this. And I want to mention, if we could run Lua on a hub, we can very likely control other IoT devices in the house, because that's what edge driver was designed to do. We still had the issue of getting a thread device to read serial number. Was there really no other way to leak the serial number? Of course not. We found that it also leaked the serial number in MDNS. As you can see, we can get the device UID and serial number from MDNS. At that point, our exploit was nearly perfect. So we signed up. Then once again, the vendor pushed an update. The update schedule is controlled server side. Our devices was updated on the last day. And the last day is 1 day after registration ended. After the updated, the serial number leaked in MDNS was fixed. Only the device UUID remained. But we still find another way. Do you remember the 443 port? It hosts an HTTP server with a certificate. If you print the certificate, you will find that, oh, the CN is the serial number. What? So, what are we busy about? In the end, we were just busy with all kind of things and nothing for during the whole preparation of Pwn2Own. But now we were all prepared, I'm sure. And we even wrote a step-by-step manual for Orange to deal with all kinds of accidents. Although there was a minor issue 1 day before the Pwn2Own. That is, the device is somehow magically block us from finish the attack within 10 minutes. Because the hub auto-updates itself during the binding process, even when it is already at the latest version, but it will still update itself. And no action required, but there is a chance the update might fail. So, we might time out in the middle of our exploit. Fortunately, the web portal still showed the device as bound to the attack's account, even while the app is still updating. So without showing the defaced web page on the device itself, we could complete the exploit within 5 minutes. So let's see the demo video together. First, we generate a QR code from the leaked serial number in CA, and we reset the machine via API. Okay, now we can bind it to our phone. Then we waited for update. In the middle of the updating, the web portal shows the device bound to our account. Then we wait for it to finish the update so we can show our web page. But when you reach 97, it suddenly dropped to 0. No one knows why. I think it's a fake process bar because it's always in a constant step. And then after binding is complete, we scan the nearby device. This behavior will trigger our malicious edge driver. And it starts a web server, then boom, Pwn by DEVCORE. Thank you. Okay. So, nice. We pwned the device successfully. And at the end, I want to apologize to Josh. He thought we did some serious work, but honestly, we didn't. I even considered we implemented the whole attack with more sophisticated techniques before this talk, but we don't have time. But this is also a great example. Many products are less secure than we assume. Sometimes simply learning a few basic techniques is enough to greatly increase the chance to finding the vulnerability. And you can do all the stupid things, but still find some vulnerability, like me. And although ZDI reported the vulnerability as a 0-day, it was already fixed by the vendor when I tested. So maybe they just forgot to notify the ZDI. And that's it. Any questions?
Thank you so much. Let's give a round of applause. Do we have any questions? You're awfully silent today. What happened to you? I have a question. You showed some soldering in the beginning.
Yeah.
Was it your first time soldering?
Yes.
Are you going to repeat this again?
I think I will. It's quite funny.
All right. Thank you so much. And let's give another round of applause. And